Let's take a look at solving differential equations. So a reminder of what a differential equation is first. So a differential equation is an equation for an unknown function that relates the values of that original function and derivatives of that function. One way that we classify differential equations is using order. An order of a differential equation is the order of the highest derivative in the equation. For instance, if we have a differential equation of the third derivative plus the first derivative plus the original function is equal to 0, this has order 3. Let's continue. Another classification for differential equations is if we call them linear, it must have this form. Some number, some function, we'll call it a sub n of x, will multiply y to the power of n. That's the derivative as a power, the order, plus another function, n minus 1 of x times y to the n minus 1. And we just continue doing this until you get to one of the original functions times y prime, and eventually a sub 0 of x times y, not y prime, just y, and that would equal b of x, and y sub n means the order n, so that, as an example, y sub 3, a little 3 like this, is meaning third derivative. And these a sub n of x formulas, so if I say call them j, and then j is from 0 to n, and the b of x formula, those are functions in terms of x. So next we'll build a little chart and we'll take a look and see some examples of differential equations, what order they are, and whether or not they fit this formula of being called linear. So I'll do the first example in blue. If you had x squared times y prime plus 3y is equal to 0, the largest derivative in there is a 1, so this is order 1, and it fits this scenario above. You have a function in terms of x times y prime, and then a function in terms of x, which is just 3, times y, that would be your final function in this list, is equal to a function in terms of x, just 0, no x's at all. So yes, this is linear. We'll do the next one in green, x times y double prime squared minus 3y prime plus xy is equal to 5. The order for this one is a 2. The highest derivative is a 2. Don't worry about the squared. What derivatives are we dealing with? So highest is a 2, and this is not linear, and the reason is you've got a y double prime squared term, and although you can have y double prime in here, at no times can you have y double prime squared and call it linear. We'll go back to blue for the next one. Y double prime equals x cos y. And so this is order 2, and this is not linear. And the reason that it's not linear is because you cannot take the cosine of a y. It's not a function in terms of y. You can have y primes, you can have y squareds, y primes, you can have y double prime, y triple prime, y's, but you can't have cos of y. You're not allowed to have that and call it linear. We'll move on to the next one in green. This one, I see a triple derivative in here, third derivative, so this is order 3. And is this linear? Well, you've got a degree order 3 term, no x's in front, that's okay, no order 2 terms. An order 1 term times a function in terms of x. So that's fine. So it can be sine x. It just can't be sine or cosine of y prime or y. You can only have y, y prime, y double prime times some amounts of x's. And then x to the power of 1 times no y's. That's totally fine as well. That's like your b of x term. So this one is yes. We're going to focus this year on first order equations, so not these second and third order. You do need to know about order and of course linear, but we're going to focus our year on just first order ones. So the simplest type of differential equation is when y prime just equals f of x, and we've already taken a look at these ones. The solution is the antiderivative. Now I actually shouldn't say the solution is the derivative. I should really replace that with a solution is the derivative, because there are multiple derivatives. When we add that c at the end, we get a bunch of different solutions that will work out. So that's going to happen quite often with these differential equations. A more general class of these first order differential equations that can be solved with integration are ones that are called separable equations, and they're always of this form. Y prime is equal to a couple of functions, the f of x function times a g of y function. That can also be written dy over dx. There's your first derivative is equal to f of x g of y. For example, dy over dx might be sine x times y, or dy over dx might be just x plus y. This is okay. That is a product, so since that's a product, that would be separable, but you can't actually separate this one out. So this one is not separable, so it is, because it is not a product, not the kind that we're going to take another more in-depth look at. Okay, to solve these separable equations, the first thing that you want to do is move all the terms that contain y and dy to one side, and then move everything with x and dx's to the other side, and then you're going to integrate. So if you start off with something like dy over dx is equal to f of x g of y, you're going to move the dx up onto this side and move the gy over to the other side, and you'll end up getting something that looks like dy over g of y is equal to f of x dx. And you'll notice that you can integrate this now. You've got a function in terms of y with dy, and you've got a function in terms of x with dx. So we can get a solution for this. Let's take a look at a numeric example of this. So I've got y times dy dx minus an x is equal to 0, or y times y prime minus x is equal to 0. And you'll notice that this is first order. You'll notice that it is not linear, and that's okay, but it is separable. And the reason that it's separable is if you rearranged this, you would see that you would get some multiplication. Y prime is equal to, and you'd have some multiplication of a g of x and an f of x formula, f of x and a g of y formula. So let's just play with this a little bit. If you add x to both sides, it would look something like this. And then if you multiply both sides by dx, you get y dy equals x dx. And now we go and integrate. So I throw my integration down there, and I get y squared over 2 is equal to x squared over 2. And then there's a constant that it comes, and the constants kind of come on both sides, but they're different, possibly. So you only need to add the plus c to one side. And let's actually just solve this for y. So if I multiply everything by 2, I get y squared is equal to x squared and 2c's. Since c is just any number anyway, 1c or 2c's is really not that much different. But okay, we get 2c's. And then if I take the square root, I get plus or minus x squared plus 2 times whatever that number is. So by solving for y, I calculated an actual final answer to my initial problem, and the final answer is what y equation fits the original statement of y times the derivative of y take away an x will always equal to 0. So you can test it out. You can take that y that we just calculated and take the derivative and multiply them together and take away an x. It will equal to 0. So again, this is a general solution because it involves c. If we wanted to find a particular solution, we can if we know, again, initial conditions. So let's take a look at what a particular solution would look like given some initial conditions in the next example. So we get an equation, solve y prime is equal to minus t times y, given an initial condition y of 0 is equal to 3. And this is often how these questions are asked. They're actually not usually asked with in terms of x. They're usually used as a variable t as your kind of x variable. And so I've got this kind of equation, dy dt is equal to negative t times y. And this is separable and first order. And linear. So we can go about manipulating this, divide both sides by y and multiply both sides by dt, and you can end up with this equation. And then integrating both sides, that gives you ln absolute value of y is equal to negative t squared over 2 plus c. And solving this for y gives you, well, this is really the exponent with a base of e. So the absolute value of y, which is y, can equal, well, plus or minus because of that absolute value, but e to this is the exponent, negative t squared over 2 plus c. And that's the same as, well, when you add exponents on the top here, you can have plus or minus e to the c times e to the negative t squared over 2. And since this value here is just a constant value, and that c can be basically any constant, this whole thing can be any constant, so you end up getting basically this part being some number times e to the negative t squared over 2. And we just call that and some number the same and some number that I used for this c up here. It doesn't necessarily have to be the same c, it's just showing that it's some number. And it's any positive number in this case. And so now I go and I use my initial value, knowing that when t is equal to 0, this is equal to 3, so 3 is equal to c e to the, t is equal to 0, so this is basically 1, 0, and e to the 0 is 1, so that tells me that c is 3, and therefore a particular solution is y equals 3 e to the negative t squared over 2. And this may seem a little bit difficult, but the steps are always the same with these. The first step that you want to do is get all the y's on one side, and dy is the dt's and the t's on the other side. Then you want to integrate both sides, and then solve for y. And a couple little tricky steps with the solving for y. When you have the initial conditions, you just need to put those initial conditions in and solve for your particular solution. So we'll practice that a little bit more in class when I see you next.